Hello and welcome to the second session of the Theory and Applications of Network Coding course. Additional advantage of network coding is that it can deliver information from source to destination node without global knowledge of the network and without coordination. So suppose we have a grid network, that we have a source node S and we have destination node T. And suppose each node in the network can only send data in the direction as shown here, and it can only send one packet per certain time unit. So of course we can deliver, so suppose source wants to deliver as much information as possible, so in this case it's possible to deliver 2 packets. And it can be done over 2 disjoint paths. For example, the source can send 1 packet over this path and another packet over this path. However, this will require knowledge of the global topology and coordination between the nodes, so they need to coordinate what they're doing. So suppose if you don't have this coordination, we might not be able to deliver those 2 packets. Suppose if each node makes a local decisions. For example, this node receives A and this node receives B and this node receives A over this link and B over this link, and just arbitrarily decide to forward B over this link and A over this link. And this is actually a good decision, but then those 2 nodes need to decide what they are doing, and each of those nodes receives both A and B, and if both of them decide to forward A because they only can forward 1 packet, and then in this case destination node will not be able to get A and B. So if they coordinate, of course they can do it, but without coordination we're not guaranteed to get it. So now with network coding, suppose each node that receives 2 packets randomly chooses some encoding coefficients that forward some random combinations over the outgoing links on the network, right? So suppose this node gets A and B and decides just to select randomly to multiply this node by 2 and this node by 5 and just forward some combination. And if this node forwards some combination, right? Then each node on the network, again, what it does, for example, this node will just decide to multiply this packet by 2 and this packet by 1, just forward the combination. Again, this node will just forward some combination of those 2 packets. So now it can be seen, right, it's not hard to verify that if each node could just kind of forward a random combination of those 2 packets, the probability that a destination node will get the same combination is fairly small. And if destination node will get 2 different linear combinations, this node will be able to invert the system and decode those 2 original packets A and B. So we'll see that network coding, and one of the major advantages, it will be able to deliver information with making just local decision, which will be just random combination, such that without knowledge of the topology, the destination node will be able to decode original packets. So this is again just to give you a taste what network coding can actually do, and the power of those techniques we can leverage those techniques to make our data delivery more efficient and eliminate need, for example, for global knowledge of the network. So now let's talk about advantages offered by coding and network coding in the context of distributed storage. So suppose we have 4 disks and we need to store 4 files from F1 to F4, and suppose we want to implement a system that stores those files with certain reliability. That is, for example, we can tolerate 2 disk failures, so we don't want to lose any information for any failure, like even in the presence of a failure of at most 2 disks. Or we can retrieve files from F1 to F4 by accessing any two disks in the system. So suppose we do these operations are here over some finite field. So suppose, for example, it can be a field of operations modulo 7. Okay, so first of all, we can verify that I can decode all 4 files by accessing any 2 disks. For example, if I'm accessing those 2 disks, then I have 4 linear equations with 4 variables, and it's easy to verify that all those equations are independent, and I can decode all files from F1 to F4. For example, from those 2 files I can decode F1 and F2 because they're linearly independent. For example, I can add those together and get 3F1. So I can decode F1, I can decode F2. If I decoded F2, I can decode F4. And if I decoded F4, I can decode F3. So it can be verified that it can be done by accessing any two disks. I can decode all 4 files. And of course, coding offers a big advantage here. We wouldn't be able to do it without coding. We won't be able to achieve this property with this limitation if we want to store just 2 files and any one of those 4 disks. We will not be able to decode all files by accessing any 2 of them. And it can be, again, easily verified. And this is basically was realized long ago and used in schemes like arrays to ensure that we ensure resilience to failures and to save storage space. So network coding offers an advantage in terms of rebuilding the system when disk fails. So for example, what happens if one of the disks fails? So for example, this disk failed, and I want to rebuild the system, so I'm putting another disk. So I purchased another disk, but now this disk is empty. So I want to regenerate this knowledge, regenerate files stored on those disks. And one of the way of doing this is to upload to download some data from unaffected disks, right? So I want to download something here. So traditional methods, if I want to obtain those combinations, so I want to obtain F2 plus F4 and F1 minus F2. So traditional way of doing this would be download enough data so I can decode all of those files from F1 to F4 and then to compute F2 plus F4 and F1 minus F2. However, to do this, I need to download 4 files. So suppose each file is 1 gigabyte. So I need to build 2 gigabytes of data because I want to restore two files stored on the system. And the question that can be asked, can it be done in a more efficient way? So do we really need to download all data to be able to restore just 2 gigabytes of data? Do I really need to download 4 gigabytes of data? And it turns out the answer is no. So if we do smart code constructions, actually we can download much less. So this is one of the solutions. So to here, to rebuild again those 2 combinations, I need to download just 3 files. So if each file again is 1 gigabyte, so to decode it, I just need to download 3 gigabyte to rebuild 2 gigabyte of data. And the idea is, for example, this node, instead of sending all data stored in those nodes to this new node, it's first perform some manipulation of this data. So first what we do, we take F1 plus F2, which is stored in one part, and add it to F3 plus F4, and we obtain a combination of sum of all those 4 files. So the same here, what we do, we will add them together, and we will get F1 plus 2F2 plus F3 plus 2F4, so we're sending it over here. And the same is obtained here, so we send it over here. And then we use those 3 combinations to obtain those original files. And again, this file, for example, can be obtained by taking this file and subtracting this file, right? So we get 2F1, so minus F1 it gets F1, F2 minus 2F2 will get minus F2, and then we get this cancel out, F3 plus 2F4, it will cancel out. And similarly, we can obtain F1 plus F4 by subtracting this from this, right? So if we take this and subtract the first combination, we'll get this combination. So now we'll see that we basically can restore this data without necessarily decoding original 4 files. And this can be done by performing decoding operations. So instead of sending nodes, instead of sending data uncoded to the new disk, we we perform some combination and sending coded combinations, and this way we minimize the amount of data that needed to rebuild the system. So you can see that clearly benefit from this. Another benefit of network coding, we can consider really a small example. Suppose we have some switches connected into um, ring network. And suppose we have some data, so for example A, B, C, and suppose I want to rebuild redundancy. So suppose I want to compute and store A plus B plus C here. And once so this it's called a parity disk, and parity allows us to basically improve reliability of the system, so the system will be resilient, will not lose data in case of any failure of any disk in the system. So to rebuild this redundancy, I need to compute A plus B plus C. So one way of doing it is just to take to download A, download B, and download C to the system, right? And again, in this case, we need to use some of the links here more than one time. Another idea would be just to use network coding. So if we send A here, so this node can add, so this node can send A. And again, it doesn't really send entire A because it can be a huge file, but I divide it into packets. And then, for example, I send A1, so basically sending a sequence of packets. Okay, let me just try to denote here A1, A2, A3 over this link. So this node will add here packets of type B. So now it will have A1 plus B1, A2 plus B2, and plus B3. And again, it can be just as simple as just exclusive OR. And this node will add C. It will send A1 plus B1 plus C1, A2 plus B2 plus C2, and so forth. So now this the final node will be able to receive this coded data. And again, it will be saving in terms of amount of data transmitted because we just add, so basically we're not forwarding data, we're just taking existing data, adding something to it, and forwarding it, and realizing saving this way. So this is another advantage of using network coding for storage. Again, we'll talk about this in this class, and this is just to get a taste of how it's done. So just kind of a brief discussion about relation between network coding and different other fields. So as we see that network coding is definitely related to coding theory, and in some way it generalizes coding theory. It's related to information theory, so we can establish several links. We saw that it's related to wireless communication, and those are two applications area that most promising, at least now. So it's storage networks and wireless networks. Also, network coding can be useful for content distribution network. We'll discuss it extensively in the class. And also it relates to areas of discrete mathematics, like combinatorics and matroid theory. So as we see, to summarize this lecture, so network coding has a broad range of potential applications: networking, communication, and distributed computing. We saw some examples in wireless communications. It uses techniques from different fields. And the advantage we saw today, a couple of examples that we improved throughput. We will see in the class advantages in terms of robustness to failures, reliability, and security. And also we saw example today in terms of delay. So network coding actually in certain conditions can improve the delay that receivers can get data from the sources. So topics in this class, so we'll first start with introduction to network coding. We already started today. Then we will talk about advantage of using network coding over techniques that don't use network coding. We will talk about relations to error correcting codes and erasure correcting codes and general coding theory. We'll talk, this is area which was actually started before network coding. It's called diversity coding, where we send data over diverse disjoint paths, and this data will be reconstructed in the source in a reliable way. Then we will start to reason about construction of network coding schemes, and for this purpose we will present algebraic framework for multicast. So in general, in network coding related areas, that can be divided into two kind of main sub-areas. One is multicast and everything else, and multicast problems are relatively well understood, and one of the way of dealing with them in this algebraic framework will be used for establishing both random codes and deterministic network codes. So again, we'll talk about that in many cases we can use randomized algorithms, and especially in the terms of multicast. And that's one of the beauty of this area, that in many cases the network codes can be constructed through a random algorithm. Then we'll talk about efficiency and how to construct network codes in polynomial time. Next topic will be undirected networks. So on undirected networks, we have flexibility that we can send data in both directions, but typically we have some upper bound on the amount of data that we can send in both directions, right? And this creates an additional level of complexity, because we need to have a decision how to use the links and which directions, and also we'll see some connections to combinatorics and graph theory. So this will be topic. Then we'll talk about complexity in terms of number of coding nodes. So each node in the network that performs coding, it's associated with certain overhead, so we want to minimize it in general. So we'll talk about how to construct a coding scheme with minimum amount of coding nodes. So we'll talk about this. Then we'll talk about using network codings for building reliable and robust networks. So we'll talk about how network coding will be used for quick recovery from link failures. And the next topic will be using network coding. How we can hide data from hide information from adversary by using network coding techniques. Next topic will be using network coding for wireless communication networks. We saw again example in this lecture, but we will expand on this and we'll reason how to use network coding for utilizing broadcast property of the wireless spectrum. The next area will be a fundamental problem in wireless network coding. It's called index coding. So we'll talk about index coding, its relation to other problems, how, for example, nonlinear codes have advantage over linear codes, and so forth, right? So we'll analyze this problem in great detail. Then we'll talk about second, is called wireless information exchange problem. That's another popular problem that we can present an algorithm. Unlike index coding problem, which is computationally very hard, wireless information exchange problem is much more tractable. So next topic will be discussion about using codes for network storage and construction of regenerating codes. Again, those codes will be used to minimize amount of data that needs to be delivered over the network to rebuild a failed parity node. And then we'll talk in general about application of network coding techniques and how to make them more practical. This will be the last topic. Okay, thank you very much. This will be the end of the first lecture, and we'll continue our discussion later on. Thank you.